This video, we'll take a look at a concept referred to as infinite limits. So we're still going to be computing limits, but now we'll have to throw this idea of infinity in with the concept of a limit, right? And in fact, the concept of infinity shows up several times as we study limits, and this is one of those times. So to give you an idea of what this entails, let's look at a pretty simple rational function. I'm just going to take the function x minus 3 over x squared minus 9, right? And we're going to ask ourselves this question, what happens to f of x to the function as x approaches, let's say it approaches negative 3, right? And let's use this relatively simple function and incorporate all the different techniques that we've used up to this point when exploring limits. And the first method that we looked at was numerically. So what I'm going to do is I'm going to make two tables. So we're going to look at the limit numerically. And I'm going to make the tables vertical. So I'm going to do this. Now, if we're approaching negative 3, we can approach negative 3 in different ways. We could do like negative 2.9. and then negative 2.99, negative 2.999. I'll do one more, negative 2.9999. And we can continue this if we wanted just by adding more nines after the decimal point, right? Well, again, if you wanted to, you could go ahead and pause the video, use this function, evaluate it, and then see if you'll get the values that I'm about to write down. So it turns out if you plug negative 2.9 into this function, you're going to get a value of 10, believe it or not. If you plug negative 2.99 into this function, you're going to get a value of 100. And what happens, again, quite remarkably, each time I add a 9 after the decimal point, the function value is multiplied by 10. So the next function value is 1000. The next one after that is 10,000. And you might guess if we were to go negative 2.99999, we would have 100,000 as our function value, right? So what does this mean? So right below that table, I would say, now, as far as on the number line is concerned, negative 2.9 is bigger than 3. In fact, all of these values of x are bigger than 3. So this is actually saying that the limit, let me get a little bit more space, as x approaches negative 3, but from the right of this function, you know, how do we make sense of this? It's not like we can't say that the y values are getting closer and closer to any specific number, right? It starts at 10, you know, and after a few steps, the function value is now at 100,000. Like, what does that mean? So kind of think about that, and we have to think about what could we write there that would be consistent with what we were observing in this table, right? And then similarly, let's say we have our table like this, and we now want to have x approach negative 3, but from below. So we would need to take values of x that are less than negative 3, but get but are relatively close, right? And they continue to get closer and closer. So we could do something like negative 3.1, and then negative 3.01, negative 3.001, and then negative 3.0001. And I'll do it one more time, negative 3.00001. And it turns out if you evaluate this function at x equals negative 3.1, you are going to get a negative 10. If you evaluate it at negative 3.01, you're going to get a value of negative 100. And the same pattern of multiplying by a factor of 10 with each additional zero after the decimal point, it occurs. So negative 10,000, and then here negative 100,000, right? And again, we're left with this question: what would we say about this one-sided limit, right? Again, what's going on here? Well, in this table on the left, the function values are getting bigger and bigger and bigger in a positive way. So these are big positive numbers by the time you get to, the fifth row of this table, right? Similarly, this is a big negative number, and actually we could continue to get larger values, either positive or negative, simply by adding more and more nines after the decimal place. And again, I encourage you to kind of explore on your own and see what happens. See just how big you can make this number. How big of a number does your calculator allow you to obtain by just keep adding more and more nines after, or similarly here, big negative numbers. Well, there is a concept in math that allows us to describe what we're seeing here in a very precise way, right? And it is the concept of infinity, right? The problem that some people have when trying to understand infinity is that they try to treat infinity like it's a regular number, but it's not a number. Infinity, this is a concept, right, that represents something that is, never ending, right? So it has no end to it, unbounded, right? You can't put a cap on it. As I was saying, I could continue to make these numbers large and positive, or large and negative, simply by using the appropriate x value. So again, infinity is not a number, but it is a concept that represents something that's never ending, unbounded, limitless. There's no limit to it, right? And that's what we're going to use to represent what we're observing here. And of course, we have a symbol for infinity. It's our nice little, it's like the number 8 that's, taking a nap. So when we see something like this, where as our x value is again getting closer and closer to a number, in this case negative 3, if the function values are getting large and positive, we're going to indicate that by writing this, right? You could even put the positive infinity. You could put the plus sign in front of the infinity if you wanted to really say, yes, these numbers are getting larger and larger and larger, but they're remaining positive. Similarly here, to indicate this sort of pattern in our function values, again, as x gets closer and closer to negative 3, we would say that the function value is approaching, or is getting closer and closer to negative infinity. Now again, even when you say that, that's not very precise, because negative infinity it's not like a fixed thing that you can get close to. It's just the idea that your numbers just will continue to get larger and larger and negative, right? So negative large numbers. And I guess you could say that negative infinity is the most negative large number there is. But again, even something like that, you could pick at it if you really wanted to get philosophical about the concept of infinity, right? So that's what it looks like in in numerical terms. Now, what would it look like in graphical terms? Suppose I wanted to graph this particular function close to -3. So think about these numbers on your x-axis, right? Like the -2.9, -2.99, and then the -3.1 and the -3.01 and so forth. And then think about where these numbers would be on the y-axis: 10, 100, 1,000. In fact, we probably couldn't even, I mean, we could set up our, we could use a strange like logarithmic scale if we wanted it to fit nicely on our graph. But yeah, just think about these numbers. You think of 10 compared to 100, compared to 1,000, and then 10,000 and 100,000. It wouldn't even fit nicely the way we typically draw our graphs. But let's attempt it anyway, right? So in fact, let me scroll down some more. So now we're going to look at it graphically using the data that we just obtained. And it's not going to be super precise because of what I just said in terms of, needing a not so standard scale to be able to plot these numbers. But let's see. So let's say this is -3, right? Then let me write that more clearly here. This is -3. And if I want to, let's take the limit from the left, So for these values of x that are close to -3, but just a little bit bigger than, let's say it starts out at 10, and then 100, and then 1,000, and then of course it's off the chart at that point, right? Even this isn't realistic. But the whole idea is that as my x gets closer and closer to -3 from this side, my y value just skyrockets. So it goes up like that. What about on the negative side? Well, something similar would happen. But now these are negative y values. So negative y values would go below the horizontal. So again, there would be a nice symmetry in this type of graph because of, these y values are just the negative of these y values. So these basically get reflected down here, and then like here, and then like here. So you have a kind of pattern that looks like that, right? But what happens is, because as far as the limit is concerned, we never actually get to -3. It's like there's a fence there. So it's almost like if I were to draw the vertical line at x equals -3, so that's the vertical line, x equals -3. It's like it would be this fence, and part of the function shoots up this direction, as we said earlier, going off to positive infinity. And then this part of the graph kind of shoots off in the negative direction, going to negative infinity. And so what does that actually mean about the line x equals -3? Well, just graphically, it might remind you of something from algebra. It's this vertical line that the function gets arbitrarily close to. And this is just a fancy way of saying we can make it as close as we want. Again, just like in the table, by making this by adding either more 9s here or more 0s here, and then causing the y value to be even bigger and positive or bigger and negative. So this blue line, so I'll just write over here, note that in this particular case, this function, x equals -3, you do remember the phrase that we use to describe such a line, right? The phrase is a vertical asymptote. Right? And so graphically, that's what happens. So vertical asymptotes correspond to these infinite limits, right? So let's kind of summarize what we just observed numerically and graphically. So when the limit as x approaches a plus of f of x, it is either plus or minus infinity, and or the limit as x approaches a minus of f of x is also plus or minus infinity, what we say is, we say that f of x has an infinite limit. So f of x has an infinite limit at x equals a, right? And all that has to happen is that the function has to go off to infinity in at least one direction. It could be both, like we saw over here, you know, the negative infinity from the left and then the positive infinity from the right. But it has to be at least one of the one-sided limits where the function gets arbitrarily large in a positive or in a negative way, right? So that's what an infinite limit refers to. Graphically, an infinite limit means the function has a vertical asymptote at x equals a. So let's write that down. So graphically, f of x has a vertical asymptote, right, at x equals a, right? Okay, so it's not a difficult thing to observe if you have a table or a graph in front of you. But what happens if you try to evaluate one of these infinite limits using only algebra? So let's go back to using this same example. So let's now look at it algebraically. And how can we make sense of this? Well, so let's see. It's the limit as x approaches -3 of let's do the one-sided limits first. And the function is x minus 3 over x squared minus 9, right? So this is a rational function, and if we're trying to evaluate it algebraically, well, we try to plug it in. So what I'm going to do is I'm going to take the limit of the top, right? So 3 plus of x minus 3. Oh, and I forgot my negative sign here. Let me fix this. 3, oh, so minus 3 plus. And let's see what happens. Well, if we plug -3 in here, you're going to have -3 minus 3, so that's -6. That's not bad. But at the bottom, if I take the limit of the denominator, so -3 plus, so -3 plus, and the denominator is x squared minus 9. If I evaluate this, I'll have -3 squared minus 9. Properties, order of operations, we have 9 minus 9, that's equal to 0. So what we end up with is division by 0, but unlike our nice indeterminate form, we don't have a 0 on the top, we have a non-zero number. So instead we have this, right? And again, this is where the concept of a limit is really important, because what this, even though we might write it as -6/0, what this is really saying is that the numerator is approaching -6, so it's getting closer and closer to -6, and the denominator is approaching 0, which means it's getting smaller and smaller and smaller. So what you end up having is a number that's close to -6 being divided by a number that's close to 0, right? So in other words, right, it would be something like this. So -3 plus means that I'm just a little bit bigger than 3. I'm bigger than -3. So that means the denominator here it would be a small, but let's see, it would be a small but and positive number. Let's see, would that be right? Actually, no, a small and negative number, right? And you're dividing, so you'd be dividing numbers like -5.9 by 0.01, something like that. So your denominator is getting very, very small, whereas your numerator is approaching a fixed constant that's not 0. And if you take a fixed constant that's not 0 and divide it by a small number, that's what leads to something very, very large. Try it on your calculator or something that you can graph with. You'll see those y values get either very, very large in a positive way or very, very large in a negative way. So algebraically, what's gonna clue you into the fact that this is an infinite limit is where you have a non-zero number in the numerator and you have a 0 in the denominator, right? So algebraically, an infinite limit right, has a numerator that approaches a non-zero constant, like -6 or 10 or a half, right? And a denominator that approaches 0. All right. So and we will in the next video, we're going to take a look at some specific examples of how to evaluate it algebraically. But I just wanted to do this one to show you this is an easy thing to observe, and it's slightly different from our indeterminate form. The indeterminate forms involved having a 0 in the numerator and a 0 in the denominator, right? So let's just kind of summarize. So yeah, let's do this summary as far as the algebra is concerned. When you take the limit as x approaches a of f of x, and you're doing it algebraically, well, there are three possibilities. If you get a real number, So I'm just going to say, you might remember that number as a real number, or I'm sorry, that notation as a real number. Then that number is the answer. So if you plug it in and you get a number, you have your elementary function, and you try to evaluate it as we've done previously, and if you get some real number, and that's going to be the answer. If you end up with a rational or some kind of fraction where you have a 0 in the numerator and a 0 in the denominator, then what you have to do is essentially do more work. Right? And what do we mean by that? You might have to factor, or you might have to rationalize, or you might have to do long division, etc. So all those algebraic tricks that we've gone through. But again, this just means indeterminate, and I can't stop here and say what my answer is. Now, if you end up with something like a over 0, where a is not 0, then this is now our third case, and this is what so the answer is, well, not the answer, but this tells us that we're working with an infinite limit, and what we have to decide is this. There are three possible answers for an infinite limit. It's either positive or negative infinity, as we saw earlier with the table and with the graph, or it is possible where we'll have something that's undefined, right? And in subsequent videos, we'll take a look at how to identify whether the infinite limit is positive, negative, or if it's undefined, right? So this is kind of the three possibilities that can occur when you're evaluating a limit algebraically. Either you get a number and that number is the answer, you get that 0 over 0, which we refer to as an indeterminate form, which means you just have to do a bit more algebra, or maybe a lot more algebra. And then the third case is when you try to evaluate it. If you have a non-zero number divided by 0, then we will look at the process for identifying when it's positive or negative infinity, or when it's undefined. So if you want to see that now, tune in to the next video. See you then.